figure out where are the areas of research in machine learning that are relevant and beneficial to both communities, and how might collaboration between these two communities really accelerate discovery and innovation. So I'm wondering here how many people know about CineGrid? Well, then I can pretty much go past the slide. And really pushing things way beyond or way in front of what the commercial implementation was to be. And people were able to do proofs of concept to really explore where were the choke points, where were the where are the areas that they really need to focus on to mitigate any problems around that real-time collaboration. And so moving forward, having accomplished pretty much what CineGrid set out to do, all about bigger, faster, better, now the question is, what's the new direction? What are the grand challenges? And doing a lot of research and discussions with people within the CineGrid community, what we call friends of CineGrid, we've all kind of gravitated to this concept of machine learning and AI as kind of being the new frontier on a lot of different levels, both in terms of getting back to the very sort of cellular nature of what we do, in terms of, what is visual perception? How does our sensory systems operate, both in terms of oral, hopefully olfactory, at some point. How do we really explore what the essence is? It's kind of like looking at DNA and understanding, huge concepts, solving huge problems by having this knowledge. And so I think it's going to be an interesting day, and hopefully there'll be a lot of interchange between people. And as I said, you have the agenda, so I don't have to go into this great detail, but we've got a great group of presenters, and we're going to have a panel with those folks. And really, as I said, David Arbuckle kind of started this yesterday with his really, I thought, really thoughtful and discussion about his team's implementation and how they were really able to create a DevOps environment where there could be changes implemented very quickly to really do a very mission critical job of delivering high quality content to customers. That's not an easy thing to do. So with that, I'd like to introduce Larry Smart, who's going to talk a little bit about the synergy between the PRP and ChaseCI and CineGrid itself, because this is really where it all happened. This is where it all started in terms of garnering the people and the resources to really make some incredible advancements. So Larry, I'll hand it over to you.
Thanks, Louise. So, I look back, I was talking to Lauren yesterday, 30 years ago, when I helped bring supercomputing to the academic community, which led to the network and the web, we brought scientific visualization. Here at 2000, the network was really the next big thing, and that's when CineGrid was founded. Now I think it's data and machine learning, and so that's what we're building infrastructure. Change was we in 2010 codified the idea that you needed a separate network on the campuses for scientific big data. Now in the media world, what this turns into is actually private global networks to move the bits from one production site to another on a 24-hour cycle. And as you'll see, that's very similar to what we have. A fundamental change, NSF never funded networks on campuses until the last 5 years in the United States. So all these campuses that have been funded now to have 10 to 100 gigabit optical diagram, accurate diagram from John Hess at CineGrid that shows who is involved with a specific research platform, all the way from the gray 10 UC campuses and Caltech and Stanford and USC, involving NASA Ames, Lawrence Berkeley Lab, and then down to where we are, up to the University of Washington, over to Korea, Tokyo, Singapore, actually Australia, Guam, Hawaii, and then to Starlight in Chicago, and on to Netherlands, and in fact, through internet to Clemson. So there's a lot of campuses that are involved, but this is a prototype, a small subset of all the campuses in the United States, which presumably over the next 5 to 10 years, the National Science Foundation will fund building a true national research platform. But we started with these, and we got more than enough to do today. And we said that the main innovation was really how do you terminate an optical fiber that's coming in with 10,000, well, 1,000 times, say, the normal amount of bits per second they're used to getting. And so these things are rack mounted PCs that are ideal, that are under $10,000 typically, but they can be extended to multi-core CPUs. You can put 32-bit NVIDIA GPUs in the slots. It can use non-volatile memory to have more, even faster than the solid-state disk, and then up to 160 terabytes of just rotating storage. We're working on getting these things down to under $1,000, and if all you want is a gigabit, then we can do it for $250. So we've deployed these videos. This is we also had a lot of talk yesterday over on how Kubernetes, the open source orchestration software from Google, has already made its way into the video industry. It's certainly something that is revolutionizing the ability to run distributed computing systems, which this of course is. And so is Google's set of data centers around the world, which is what led them to develop it. So here with these Fionas, we're able to deploy several petabytes of rotating storage, but tied together at 10 to 100 gigabits a second. So it's essentially like it's in the same rack, except it's distributed over a international footprint. And then we use Rook and Ceph, as we had some discussion yesterday about that, for the distributed object storage space. Now there are many techniques we saw. We can go in, each of those blue dots is a router or some other device along the network path. And so we constantly monitor in real time the complex set of network paths that connect these Fionas, and they're colored. See the red in there? That says that there's that for whatever reason at that moment in time, that leg is not working. And of course, this is just a subset of California of all the Kubernetes nodes that we have. Kubernetes enables us just by putting our software, including, by the way, for Sonar and Grid FTP. So we've actually taken the measurement software, which usually have a dedicated hardware device, containerized that, and now we can send that out as part of the Kubernetes software. Well, this allows us to have these MAD-DAG DOE developed. Each of these is a row and column as an endpoint. That is one of our Fionas. And we can measure different things. So for instance, this one is measuring the trace route. Are there multiple routes showing up between the endpoints? Or over here is the packet loss along between the two. So we use these to debug the overall performance of this distributed system. Now, what this has allowed the scientists to do, and again, we have probably 50, 75 top scientists in everything from particle physics analysis to bioinformatics to telescope surveys to earthquake engineering, climate science. I don't have time to get into all that, but I'll just give you one. This is part of the worldwide optically network connected Large Hadron Collider data transfer node. You can see that he's sustaining 30 gigabits a second for quite a long period of time. And so he's now moving to 100. And this is, by the way, flow going from the 5th floor of the physics department to the Fermi Lab, which is the tier 1 center for CMS for the United States. And then all that came from Geneva. We had a really nice talk yesterday by Shadong from Santa Cruz about just how rapidly this is growing. So by next year, the large synoptic survey acts as its basically the compute engine. So what it's doing is it's looking in the sky and NCSA where it compares with the night before. If there's anything that changed its magnitude, its color, or its position, that's an event, and then it sends out alerts about that. Well, this thing is tracking 40 billion objects in the universe. It's basically turned the entire universe, the observable universe, into a video. And it's just looking for motion or change, right? And it will produce 1 to 10 million of these events a night. And when I was doing astronomy, and I was sitting up and freezing my ass on the mountain, doing optical or radio telescopes down in Socorro, New Mexico, you know, we called these event notifications telegrams because that's how they actually were sent around. Meaning there'd be one every few weeks or something, not one. So in terms of machine learning, just sorting out where you're going to point your telescope when you get 10 million alerts is going to become a new example of using that. For instance, as Shaw said, you know, it's like news when we discover a supernova. You know, you hear about it on the radio or TV. You see it 1,000 a night going to be discovered. This is a complete change to the way we think about astronomy. Now, the same is going on in Earth observation. So John Delaney, who's a longtime colleague of mine at the University of Washington, had the vision for what eventually became the Ocean Observatory Initiative from the National Science Foundation, repurposing fiber cable that is laid, subterranean fiber cable that can both send electricity, like 10,000 volts down to the ocean floor, in this case a mile down, and also fiber coming back. And so that was deployed over the last decade or so off the coast of Portland, off of basically Oregon and Washington. And there's an axial volcano, there's a spreading center, the Juan de Fuca plates, where 3 plates come together. And as a result, there are these hydrothermal vents. And this is, as you can see, a collage of HD cameras. So how do they photograph this thing? Well, there's a robot down there. There's an ROV that is coming back up to the surface with a fiber cable. And so it goes around this thing, swims around it, basically take these pictures. And so this is a very large collage of this thing, again, a mile down. This is 40 HD frames. Then every 3 hours, there's a window in which they do a 14-minute video, live HD stream from a mile down. And of course, this thing makes a great use of the wall next door, which has got 65 million pixels. And so this was John actually blowing up that collage. However, we were also able to, when he was there, he had his guys who were the technical people. And I said, well, you know, when is it going to be that the time is going to come that we can do we can see the video? And he said, oh, why wait? And he pulls out his laptop and clicks a few things, and we are seeing live from the ocean floor HD video. And he's controlling the robot. And I said, are you sure you want to do that? I mean, what if the robot bumps it or something, you know? And he says, nah, I do this all the time. It's no problem. I said, don't you need to get permission for this? He says, yeah, you're supposed to, but anyway, of course, he knew exactly what he was doing. And what you can see here is just this stunning way that we're going to be able to have observatories all over the planet bringing back these kind of images. Those filaments are bacterial. There's the water coming out of the hydrothermal vents is much greater than boiling at the surface and very mineral rich. And there are microbes in those tube worms that convert that into the food that then the tube worm lives off of. It's chemical synthesis. That's not photosynthesis. No photons down there. So this is the thing that I think is fantastic. That we're really flowing these kind of and he and his team, of course, built the fantastic ones you've seen here. But then we've been working with Jeff Weekly at Front Row, building the one at Merced, and now we're able to basically share common 3D spaces over the optical fibers so that both places can go in the people in those caves can share in the experience of investigating those spaces simultaneously. I think that's the sort of thing you're going to see a lot more in the consumer world as well. By the way, the sun cave that you saw, everybody's, Mark Zuckerberg, it's going to be Oculus Rift. We're going to really, all share. This is the next big thing he said in communication that's going to happen. Well, the sun cave is 250 times the number of pixels that are in an Oculus Rift head-mounted display. So you're seeing sort of there what you might see 10 years from now or something. Now, another thing is object databases, which a lot of things in media are using. We have an example of that where we're connecting two major centers, one at San Diego, Center for Western Weather and Water Extremes, and one at Irvine. And these are both led by top level people. The one at Irvine is actually tracking all major precipitation events in the world and then keeping track of them. And then the one down here is seeing how does that convert the precipitation events over the Pacific into things like atmospheric rivers that come across and make these torrential downpours, or not, in which case we have droughts. And so it, trying to predict that. Well, they have to move these data sets back and forth. And so they put together their computers at Irvine and here over the Pacific Research Platform. And what originally took 20 days to do one movement and then work on now is 20 hours. And we hope by the end of the year it'll be 20 minutes. So that means and if you imagine you're doing this and it's like how much you can get done per the digital dailies, right? I mean, but how much can you get done in that 24 hours? Well, here you can get one move a month versus one move a day versus one move an hour in terms of what this speedup does. Now, I won't go into the details about this, but what's interesting to me is that they are forming, they take, you may remember that one of the things that we got famous for in CineGrid visualization was the thunderstorm animation that Bob Williamson did at NCSA. So these are convective events. So the sun heats the surface of the earth, it makes a convective updraft, and that creates this precipitation event, tabletop and everything. Well, now imagine that thing is going through going at like 50 or 60 miles an hour across the plane. That's a space-time object. So now take that entire development of that space-time object, and that's an element in your object database. Now, what you want to do is to go back into all those and figure out where was the event that started that precipitation event. And so what they're doing is using machine learning on this vast, because they're keeping track of every precipitation event in the world for like years. And so they got to go into that. And that's an example of why we're putting machine learning now on the Pacific Research Platform. We work with Scripps Institution of Oceanography here. You know the famous pier. Well, there was fiber out to the end of the pier. I funded it to go into water. And then what you could do is they developed this microscope where they could actually look at the amazing phytoplanktons and zooplankton, the base of the food chain, and most of what generates the oxygen you're breathing right now, and get these images. Well, they've got over 1 billion images now. And so what they're doing is using the Fionas for image processing, and then going in and doing image recognition, just like Google and many others have been doing. But in this case, instead of figuring out that you can identify cats, which we certainly know how to do as humans, what you're actually doing is we didn't know how to do as humans, which is to track the detailed development in time of the ecology of how many species there are of these things as the ocean acidifies because of the continued addition of CO2 to the atmosphere, most of which is taken up into the ocean, thereby making it more acidic. And these things, of course, have calcium carbonate shells, which then dissolve in enough acid. So this is like suicidal as a species for us to be continuing to produce CO2, but that's another talk. Anyway, so we have then got another NSF grant to put machine learning on top of the Pacific Research Platform. And these are the universities that are involved. What we did is we found machine learning, statistical machine learning algorithm developers, the computer scientists and people like that. And we have 30 of those across these 10 campuses. And we are then deploying 206 of these in the field, and then tying them together along with this several petabytes of data. And so these yesterday, Ken Prescodata, who's my colleague here at UCSD at head of our recognition lab, went through these. I can give you a short list here. 6 different modes of this machine learning. All the deep learning you're hearing about multi-layered neural nets is in one, but there are all these other things that you do as well. So here are all of the faculty and staff, and whether they work on one or another of those 6 different modes of this machine learning, there's 15 more. So we have pulled together almost unprecedented set of academic frontier researchers, new algorithms, and new applications of this. But in addition to having this distributed set of GPUs, of course, there are the 64-bit double precision GPUs that are at Amazon Web Services and in the NSF supercomputer centers. There's, as I said, 288 here, just in the common supercomputer of those 64-bit Tesla GPUs. But this is the big thing now, is the emergence of non-von Neumann. So GPUs and CPUs are both von Neumann architecture. But what's changing is the coming of things like the TensorFlow accelerators, GPUs, which are ASICs that have been developed by Google, and these are just clips from the media talking about this, how this saved Google having set up a whole set of data centers around the world once the CEO said we're going to put machine learning in everything Google does. But it's not just Google. And we're right now, in fact, last week at the Internet Global Summit, we were actually documents Texas, FPGAs, 432 FPGAs, which are non-von Neumann accelerators. And Microsoft, as you know, for Bing, accelerated Bing by putting one of those Bing servers and now it's applying the others. So we're doing a lot of research here on new then they, largely because of Microsoft, they bought Altera, which is a major FPGA. They bought the San Diego startup Nirvana, which is a machine learning accelerator. And they had them for some time and continue to be working on their own GPUs. Intel is the company that's capable of integrating all of this. The CPUs, the GPUs, the multiple types of machine learning accelerators. Whether they will or not, I have no privy to, but stay tuned. So my point is that industry is way down this path because they see this giant exploding market of the application of machine learning in the commercial world. And what we're trying to do is to bring that to the academic innovators, keep feeding innovation into that commercial world. So I'll just end with the fact that as part of our NSF grant, we're supposed to look forward to what lessons we've learned here would inform a later national research platform, a full-scale one. And we had a meeting well attended last year in Montana, and we've got the second one coming up engagement for Internet 2. And so we invite all of you in August to apply.